Okay, so can everyone hear me? Okay, cool. So telling you about neutrinos and cosmology again, but except that this time it's in more detail. So basically the idea is that I want to tell you how neutrinos fit into this grand scheme of things in the history of the universe. And here's the plan of how I will, oh, this is kind of loud. This is the grand plan of the grand lecture plan. Okay, so the 3 lectures will be divided into 2 parts, where in the first part, I'll tell you about neutrinos in homogeneous cosmology. So that's basically what I'll tell you in the next 50 minutes or so. And then in the next part, I will talk about neutrinos in the inhomogeneous universe. And that's the part that concerns structures and the theory of inhomogeneities, etc. Okay, so this is a bit of a funny split. So I expect to be able to get through maybe the first 2 topics here today. And then tomorrow I'll go on to talk about precision C nu B and maybe the first part of part 2 in the second lecture, and the last lecture will be the last 2 topics. So that's roughly how I see things will go. But anyway, just to give you an idea of where everything sort of fits in. So homogeneous isotropic universe is basically just background Freeman, Lemaitre, Robertson, Walker cosmology. The hot universe concerns the first few seconds after the Big Bang, whereas the inhomogeneous universe part of the lecture course here concerns mainly how things evolve in the late time universe to give us the structures that we see today. Okay. So there's some useful references that you can find. These days, there's even a textbook called Neutrino Cosmology by Lescourt, Marganeau, Miele, and Pastor. So it's published in 2012, I believe. So you can find it in the library, perhaps. There might even be a pirate PDF that I'm not supposed to share. And a lot of the stuff that I'll cover here are really kind of more hardcore cosmology than anything else. So there are some very nice lecture notes out there. Daniel Bauman's lecture notes are always fantastic. And the more detailed formalisms of how to treat inhomogeneities can be found in Seljac and Hu. The lecture notes are Googleable. There are also some reviews out there that are more specific to neutrinos. So just remember this slide and go back to it if you need to find more details on what I'm talking about here. Okay, so let's begin then. So the first part on neutrinos in homogeneous cosmology. So first of all, I'm just going to tell you a bit, give you a Cosmology 101 course. Some of you probably already know this stuff, so bear with me. Okay, so this is the concordance flat lambda CDM model, and that's the simplest model that is consistent with present observations. Okay, so it has dark energy, which is most of the comprises most of the energy density that we see today. That's dark matter and atoms. And if you wind the clock back about 13.4 billion years, around CMB formation times, then you see the energy content is a bit different. So you have mostly dark matter, some neutrinos, some photons, and some atoms. Okay, so this is the cosmological model that we know today. But how do we get to this point? Well, actually, to get to that point, we have to first start with what we call the Freeman, Lemaitre, Robertson, Walker universe. Okay, and the first assumption in this universe is called a cosmological principle. And essentially, it goes like this. Our universe is spatially homogeneous and isotropic on sufficiently large length scales. Another way to say this statement here is that we're not special. Okay? Now, homogeneous and isotropic sound like the same thing, but actually they're not. Homogeneous means same everywhere, whereas isotropic means the same in all directions. Okay, so if you look at these 3 pictures over here, this universe is isotropic, but it's not homogeneous. This universe is homogeneous, but it is not isotropic because all the planes are moving in one direction. This universe here is both homogeneous and isotropic. Okay? Now, another key word here is that the cosmological principle applies on sufficiently large length scales. And by large length scales, we mean lengths that are of order 100 megaparsec longer. Okay? Now, you're probably not familiar with megaparsec. 1 parsec is about 10 to the 18 centimeters, which is probably still kind of a bit hard to imagine. But let me tell you that the distance from the sun to the galactic center is 10 kiloparsec. Okay? Whereas distance from the Milky Way to the Virgo cluster is about 20 megaparsec. Okay, so when we're talking about cosmology, when we're doing cosmology, we're really looking at length scales that are larger, much larger than the local group, okay, local universe rather. And the size of the visible universe is order 10 gigaparsec. Okay, so cosmology is the study of the evolutionary universe between 100 megaparsec and 10 gigaparsec, essentially. Okay, now we have plenty of evidence for large-scale homogeneity in isotropy. So this here is a very nice picture of the local galaxy distribution as measured by the 2-mass redshift survey. It's a bit old, but it's such a nice picture, I have to show it. And it shows basically each dot here, it's a galaxy. And as you can see, it's pretty homogeneous. Yeah, you don't really see any, I mean, you see some small structure, small-ish kind of structures, but it looks pretty homogeneous. This black bit here is just a galactic plane, and you can't really look through the galactic plane, which is why it's all black here, but otherwise, this is pretty homogeneous and isotropic. Another piece of evidence for large-scale homogeneity and isotropy is, of course, the CMB, which was detected already back in the 60s. And they saw this 3.723 degree background. And these days, we have much better measurements. So since the 90s, we've had the COBE mission, which saw these, for the first time, these 10 to the minus 5 temperature fluctuations. And these days, we also have in the noughties, we had WMAP, which also measure these fluctuations, but with an improved resolution. And most recently, we have Planck. Okay, so the temperature fluctuations is measured by Planck, it's here, and this is the polarization fluctuation. You can compare the resolution of these 3 generations of CMB probes, and you can see how we're improving all the time when it comes to resolving these spatial fluctuations. But nonetheless, these are tiny fluctuations, 10 to the minus 5. And in the second part, I'll tell you how we can use these fluctuations to really do precision cosmology. But for now, it looks pretty homogeneous and isotropic overall. Okay, so if you have homogeneity and isotropy, that implies a maximally 3 symmetric 3 space, which means that your space has 3 translational and 3 rotational symmetries. So if I want to describe this kind of space-time, then there's one metric that does the job quite well. And that's called the Freeman-Lemaitre-Robertson-Walker, or FLRW metric, and it looks like this. Okay, so this is your line element, this is the time part, which looks kind of standard. And this part here is the space part, which is expressed in spherical coordinates. This is kind of standard spherical stuff. The only thing that is a bit different is that here you have this K parameter that basically tells you about, that basically specifies the spatial geometry. So K can take on 3 numbers. It can be -1, 0, or +1, and denoting different kinds of spaces. We live in hyperbolic, flat, and spherical. Another very important feature of this FLRW metric is this quantity here, A. This thing is called a scale factor. Now, on its own, it doesn't mean much, but it's a time-dependent function. And essentially, what the scale factor tells you is that if you take 2 scale factors at 2 different times, and you take the ratio between these scale factors, then what you get is the factor by which a physical length scale has increased between the first time and the second time. Now, another important concept in FLRW cosmology is the co-moving observer. And that's basically an observer that is at rest with the spatial coordinates of this geometry. Okay? So if you look at this schematic here, this is basically a grid in space. Okay, so spatial coordinate system. And these 4 smiley faces are co-moving observers. They're sitting at rest on the coordinate points. And if we move forward in time, space will expand. But these 4 co-moving observers are always sitting on the coordinate points. They're not moving with respect to the coordinate points. However, the physical distance between the co-moving observers, between 2 co-moving observers, has increased because space is expanding. Okay? But because these observers are co-moving observers, the coordinate distance between 2 observers is always the same. Okay? So the point here is that you need to distinguish between coordinate distance and the physical distance. Okay. Another concept is that of geodesic. And geodesics are essentially just straight lines on a curved space-time. And these are the shortest distances that particles that are not subject to any other forces would move on in a given spatial geometry, space-time geometry. So the easiest way to think about this is to think about flight paths. It's like planes usually move on geodesics. I mean, okay, often they don't because of various weather conditions and maybe political things that would cause a flight path to deviate from a geodesic, but mostly they move on geodesics. And so if you think about flying from here to I think this is maybe Seattle and this is probably Munich, you wouldn't just draw a line like this, okay? Because that's not the shortest distance. But the shortest path is actually going over Greenland, okay? And that's because the surface of the Earth is basically a curved spatial geometry. Okay. So what's important about geodesics? Well, if you have a free particle that is moving in an expanding space-time, then it is moving on a geodesic. And when it's doing that, the momentum of that particle, and regardless of whether it's a massless particle or a massive particle, will redshift, will suffer cosmological redshift. Okay, so mathematically, that's what I'll write. Okay, the magnitude of the momentum of the particle is scaling like the scale factor to the -1. So it's decreasing over time as it is moving forward. So again, illustrated by this little schematic over here, you have a fairly fast particle as seen by smiley face, yellow smiley face, but then by the time this particle gets to green smiley face, it's a little bit, has a smaller momentum and so on and so forth. Okay, so this is called cosmological redshift, and it applies to the momentum of a particle no matter whether it is a massive particle or a massless particle. Now, if it helps you to appreciate this point better, you can also think about redshift in terms of the wavelength, because as we know from quantum mechanics, wavelength is just inversely proportional to the momentum. And so in this case, you can think about this expanding balloon as your universe. And if you draw a wave on it and you let the universe expand, clearly the wave also has a longer wavelength. Okay, so that's equivalent, basically. It's an equivalent way of thinking about cosmological redshifting. Now, so imagine that you have something that is emitting, a particle, usually a photon. Let's say it's emitted by some co-moving observer at some time TE, and it has a wavelength lambda E. So this particle will move through this expanding space, and at some later time, say today, T0, this particle will be measured by a co-moving observer who would measure a wavelength lambda 0. So if I take this, actually I'm not quite sure whether it's observer or 0, but anyway, 0, whatever. If I now take the ratio of these two wavelengths, the one that is observed divided by the one that's emitted, then this ratio will essentially go like the scale factor at the initial time, at the observed time, sorry, divided by the scale factor at the time the particle was emitted. And this ratio is normally parameterized by astronomers using this redshift parameter Z. Okay, so that the longer ago the particle was emitted, the larger this Z parameter. Okay, so by definition, the redshift today is 0. Okay. So what this means is that you can essentially use time, t, scale factor a, and redshift in a way that is more or less interchangeable. Because as you move forward in time, your universe is expanding, so the scale factor goes, a also is growing, so t and a are both going forward and increasing at the same time. Whereas redshift, basically, this arrow points in the other direction, so that the earlier the time, the larger the redshift. And so what I'll be doing in this lecture and the next two will be to use time, scale factor, and redshift in an interchangeable way, and I hope that that doesn't cause too much confusion. Okay, so that's geometry stuff. Now, what about the stuff in the universe? Well, in general relativity, if you want to describe the stuff in your universe or whatever, what you'll do is to write down the stress energy tensor, T mu nu. Okay, and this is a stress energy tensor, T mu nu, and it's this 4x4 matrix symmetric, so there are only really 10 degrees of freedom in there. You can classify these different entries according to what they represent physically. So the T00 entry here basically is the energy density of stuff. So essentially the amount of energy per unit volume. Then you also have the spatial part, which is in this pink color. And the diagonal entries here correspond to pressure. So yes, the stuff may have a pressure. And you also have these off-diagonal elements here. So here, the time-space part, you have energy fluxes. Down here are the momentum density. And then in the space part here, you have T12, T13, T23, and also reflected over here. These are called shear stresses. So if they're engineers, anyone who's taken engineering, it's basically kind of shearing something. Okay. So that's the general stress energy tensor. But we want to use this to describe stuff in a homogeneous and isotropic universe. And as it turns out, the only form that the stress energy tensor can take if you demand homogeneity and isotropy is this one. Okay? You're not allowed to have anything in the off-diagonal entries because as soon as you do, you break isotropy. Okay? So the only terms that you're allowed to have are diagonal, and that's the energy density, that's fine. And as I mentioned earlier in the last slide, these three terms here in the spatial parts in the diagonal entries correspond to pressure. And since I have homogeneity and isotropy, these things also have to be the same, exactly the same, P appearing 3 times. And also, these functions here are only functions of time. They cannot depend on the spatial coordinates. Again, because we're demanding homogeneity. Okay, so only allowed to depend on time. Okay, so that's T mu nu. The next question is, having written this down, how do these quantities evolve with time? Well, the answer to that is the continuity equation. Okay? Basically, what you're doing here is to apply conservation of energy and momentum, local conservation of energy and momentum, which is a more general expression if you're looking at GR. But if you put in the FLRW metric into this expression using the T mu nu that I showed you in the previous slide, this is the equation that you would get. So this is the continuity equation that you would see all the time in a cosmological context. So it's an equation of motion for the energy density, rho alpha. Alpha here is it's a label that I give to the kinds of stuff that I have, because I forgot to mention this T mu nu here. You write down 1 T mu nu for every substance that you have in the universe. So if you have dark matter, you'll write down 1 for dark matter. You have radiation, you write down a T mu nu for radiation, therefore the label alpha. Okay? So the continuity equation, you write down 1 continuity equation for each kind of energy / matter stuff that you have in the universe. Okay? So it's d rho dt, and it depends on a number of things like how the scale factor is evolving. It depends on the pressure. Now, you may ask at this point, why is there only 1 equation of motion? Why only d rho dt? Why can't I write down dp dt as well? Well, actually, you can. You can take this local conservation of energy momentum and try to derive an equation of motion for p as well. But as it turns out, it's not linearly independent. Okay? And in fact, because the relation between rho and p is essentially something that characterizes the kind of substance that you're trying to describe, it is in fact something that you need to supply externally to the GR framework. Okay? So we have to specify a relation between rho and p. And in other words, we have to specify an equation of state for this substance, alpha, that we want to describe. And that's a property of the substance. Okay. So at this point, I'm going to introduce the equation of state parameter W. And that's basically just the pressure divided by the energy density. It can be a function of time, but in simple cases, if we assume that this is a constant, then I can just replace P with W rho. If W is a constant, then I can very easily solve this differential equation. It has a very simple solution. It looks like this. So the energy density goes like the scale factor, raised to the -3, 1 plus the equational state of the substance you're trying to describe. Okay, and this is how the energy density evolves with the scale factor. Okay. All right, so having now written down the equation of motion and also figured out a solution for the energy density and how it evolves with the scale factor, we can now ask what kind of stuff do we want to describe? Well, obviously, there's non-relativistic stuff, like people and the desk and everything that we see, so atoms or constituents thereof or bound states thereof. And as we now know, we also have dark matter, so stuff that doesn't emit light but can feel gravity. GR people like to call it dust. I try to avoid that term because I think dust can mean totally different things in astronomy. Just call it dark matter. Now, non-relativistic matter has an equational state that is very close to 0. And the reason is that the energy density of non-relativistic matter is completely dominated by the rest mass of the stuff. Pressure is essentially just kinetic energy. Okay? So this means that when you divide the kinetic energy by the rest mass, it's a tiny number relative to the energy density. It's a tiny number. Okay, so we can just say W for matter is 0. And if you now stick this expression here, W equals 0, into the expression for how the energy density should evolve, then what I will find is that rho m goes like a to the -3. Which is quite easy to understand, I think, because if you have just some non-relativistic stuff that's sitting there, it's not being created, it's not being destroyed, then the only thing that can affect the way its energy density evolves is the expansion of space, okay, the expansion of volume. Okay, and volume expands like a to the 3. So immediately you will come to the conclusion that the energy density of non-relativistic stuff must go like a to the -3. Now, we also, after matter, we also have ultra-relativistic stuff. We have quite a lot of that in the form of photons, in the form of this 2.73 degree background CMB. Okay? We also have Rayleigh neutrinos, my favorite, and gravitational waves, and anything that's just light and moving at practically the speed of light. This kind of stuff has an equational state parameter of 1/3. This is just from thermodynamics. And again, if you put 1/3 into this expression for the energy density, you will find that rho r, radiation, goes like a to the -4. So what you're seeing here, essentially, is volume expansion. And you pick up another factor of a to the -1 because the radiation, the energy, for radiation, the energy is equal to momentum. And the momentum redshifts. Okay, so you have a to the -4. Of course, you can also have other funny things in the universe that are not quite matter and not quite radiation and not quite anything we understand. And the prime candidate for that is the cosmological constant or the vacuum energy. And this kind of stuff has negative pressure, okay? And the equational state parameter is -1. And again, put this into this expression, what you'll find is that rho lambda is a constant. So in other words, the more space you create, the more energy, which is totally weird, but that's the cosmological constant. Okay, so having described these 3 forms of energy density, we can now see how you can put them next to each other and plot the energy density versus the scale factor A. Okay, so what do we have? Red here is the radiation energy density that goes to a to the -4. Blue is the matter energy density that goes to a to the -3. And clearly, because these things go like the scale factor raised to some negative power, they must dominate if A is very close to 0, okay, as A approaches 0. And in fact, the radiation density has to be the dominant contribution simply because it scales like a to the -4. But if we go further and further out here and forward in time, when the scale factor becomes increasingly large, then at some point, these energy densities will just drop off because they go like a to raise to something negative. But the cosmological constant, energy density due to the cosmological constant, well, it's always constant, okay? And eventually it will come to dominate, okay? So what we have therefore is generically a period of radiation domination at early times, followed by a period of matter domination, And then eventually we'll go into this lambda domination period. You can also define these 2 points here where the radiation line and the matter line cross. That's called matter radiation equality, for obvious reasons. And this point here where the blue line crosses the green line is called matter lambda equality. And if I now take what we have learned from observations about the energy content of the universe, then roughly we have this timeline. So we sit here today just shortly after matter lambda equality. And radiation, and by definition, the scale factor is 1 today. It's just a definition. You can choose any other number you like, but it won't make your calculations easier. So we just choose 1. And matter radiation equality is over here at a scale factor of about 10 to the minus 4. Okay. Again, if I want to embed the major events of the universe into this schematic here, structure formation takes place during matter domination. The CMB, the last scattering surface, was basically a little bit after matter radiation equality, and nucleosynthesis, so the formation of the light elements like helium-4 and deuterium and helium-3 and other trace light elements took place at a very early time when the scale factor was about 10 to the minus 8 or so. Okay. Good. Another thing I just want to highlight is that when I showed you this picture of the energy budget of the universe earlier, there were always these 2 pies, one for the composition of the universe today, and one for the composition of the universe at the time of photon decoupling. And they look different. And the reason they're different is because different forms of energy densities evolve in different ways. Okay, okay. So we have the cosmological constant, kind of taking over at late times, giving us this picture here where the dark energy is, 75%. Whereas if you go back to earlier times when radiation was more important and dark energy wasn't important, then you have this different pie showing. Okay, last thing here, I think this is probably the last equation I would show, and that's the Freeman equation. This is very important because it will come back later in the lectures. And the Freeman equation is essentially an equation of motion that describes how the scale factor A itself evolves. Okay, and this is something that comes out of the Einstein's equation. Okay, so if you want to do the exercise, you can put in the Freeman-Lemaitre-Robertson-Walker metric into the Ricci tensor and put in the T mu nu stress energy tensor, as I showed earlier. After maybe a couple of pages of algebra, you'll get this out. So it's basically an equation for A dot A, so the scale factor, derivative of the scale factor with respect to time, A dot. And this combination here is usually called the Hubble expansion rate. And as you can see, this x squared here is proportional to 8 pi g divided by 3, where g is the gravitational constant, which is the constant of any theory of gravity. And rho alpha here is the energy density of all the stuff that we have in the universe, dark energy, radiation, matter, whatever else, and you sum over all of them. And there's also an additional piece here that depends on the spatial curvature. Okay, so what this tells you is that and what forms of energy density affects the expansion rate. The spatial curvature of the space of my space also determines how fast the universe expands. Okay. Now you may have seen the Freeman equation in this form. Okay, and essentially what we're doing here is to re-express all the forms of energy densities in terms of the critical density today. Okay, and so you can define these reduced energy density parameters, and omega m is, well, okay, what is that? I can't even read. Omega alpha, and then this is the critical density, which is just 3 times the Hubble parameter divided by 8 pi g, and omega k is defined like that. And here you have 8 to the minus 3, which is how matter energy densities evolve. Radiation energy densities evolve like 8 to the minus 4. Cosmological constant is constant, and so on and so forth. Okay. Now, if I had a flat universe, what this means is that k is 0, in which case omega k would also evaluate to 0. So I have omega k equals 0. And by this definition here, what this implies is that the remaining omegas, omega m, omega r, and omega lambda, must add to 1. Okay? Now, we can simplify this expression further because we know that the radiation energy density today must be tiny because it drops off like 8⁻⁴. And in fact, we know from measuring the CMB temperature power spectrum, the 3-degree background, that omega r has to be about 10⁻⁵. So you can ignore it essentially. Okay? So it's very often in the cosmology literature to see this expression omega m plus omega lambda equal to 1 as indicating a flat universe. And that's because we've dropped off the radiation piece. Just to give you some numbers here, the current observations show that omega k is much less than 0.01, and omega m is about 0.3, omega lambda is 0.7, and x naught here, which is the Hubble expansion parameter today, it's about 70 kilometers per second per megaparsec. Okay, so this picture here illustrates the kind of universe that we live in and where we expect it to go. And so here, this is time. And the universe that we live in is the one that is indicated by this red line over here, which has a flat spatial geometry, and omega m is 0.3, omega lambda, well, it's called V here, it's vacuum energy, V for vacuum energy, but it's my lambda. It's 0.7, and so you have this, basically this open universe that expands forever. Okay? If we had different parameters, then the fate of the universe would have been different. So this one here, for example, has a huge excess of matter, the yellow one, where omega m is 5. And what you see here is that this corresponds to a closed, a curved space. And it's a closed universe in the sense that it would expand for a little bit, and then it will collapse again on itself. Okay. So yeah, so that's the universe we live in. I mean, not that we can really tell what happens, you know, in the far future, but that's, according to the model we have today, that's the expectation. Okay, this is the last equation, not the other one. What is this about? Oh yeah, this is the Freeman equation, but expressed in a slightly different form. So previously, the Freeman equation I showed you is for A dot divided by A, right? And if you square that, you get the Hubble parameter square. Here, this is the Freeman equation again, and you can again get this equation out of Einstein's equation. But this time, this is written in terms of a second derivative of the scale factor. So this tells you about the acceleration rate. And what you see here is that A double dot divided by A is proportional to negative, and then some combinations of the energy density and the pressure. And this is a nice way to illustrate accelerated expansion, because as you can see here, if you have acceleration, it means that the right-hand side has to be positive. So the way to achieve that is for rho plus 3p, the sum thereof, to be less than 0. And this automatically sets a requirement on the equational state parameter that you must have to achieve this accelerated expansion. And it turns out that your equation, if the equational state parameter has to be less than minus 1/3 if you want accelerated expansion. Conversely, deceleration means the opposite, and that sets a condition on the equational state parameter to be larger than -3. Okay, so I think that's it of the homogeneous, the Cosmology 101. Are there any questions for me at this point? Yeah. This one? No, it drops out. It drops out, yeah. Right. Okay, so, yeah.
When we say the universe is flat, so it's flat in its entire journey, or it's flat after a particular point in time?
So I didn't get that question.
Okay, so when the universe is flat, that means the universe is Euclidean in its entire journey, means from the Big Bang to now, or it's like it have some curvature and then it becomes flat after some point in time.
Well, I mean, you could be living in a perfectly flat space-time for some reason, because nature has chosen it. Another possibility is that it actually has some spatial curvature, but then it's somehow diluted away. So inflation is one way to give you that dilution. Okay, so you have this, in theory, inflation is such that you have this exponential expansion of space that is so, that stretches out space, that expands space so much that even after expansion, it takes a long time for the curvature to show up. Okay, so that's another possibility. That's why people invented inflation. Okay, they were trying to explain in a dynamical way why it is that the universe looks flat today.
And also before 1998, the value of omega is roughly about 0.2 to 0.3, the energy density.
The omega what?
Total energy density.
Total energy density.
So before the dark energy invention, so it's 0.2 to 0.3, and after that it tends toward 1. Then we say the universe is flat. So how these two measurements are correlated? Can you?
Hang on, I don't quite get that. Before 1990, well, okay, there was always the hint of dark energy had been around for a long time. And what did you say about before 1998?
Is in 19 energy.
Well, yeah, statistically significant.
Yes. So I was reading some papers and it says before 1998, the total energy density was roughly 0.2 to 0.3.
0.2 or 0.3?
0.3.
For matter?
For entire total energy density. And after the invention of dark energy, they claimed it to be nearly 1, and that's how the inflation model gets into picture, because the inflation suggests toward 1.
Well, inflation is much older than that. It's from the 80s. So maybe I need to see what you mean. Maybe you can show me what you read, because I'm not completely getting your point.
Okay.
I think. Yeah. Yeah. It is by definition symmetric. It's well, you mean this one? It is by definition symmetric, and I write 1, 2, 2, 1 because this has to do with okay. I mean, okay. It may pick up a minus sign. It may have pick up some. It might just be okay. So I should say it again. It is symmetric in the sense that you only have 10 degrees of freedom. You don't have 16 degrees of freedom. So T12 is related to T21. Okay, there may be a raising operator or lowering operator depending on whether you write T mu nu as lower indices or upper indices, or one lower or one upper. Okay, but they are related. They're not independent. They should, for both lower, they should be the same, like G mu nu lower, they should be exactly the same. But they can have different interpretations. So normally people say that this is like these are momentum density, just how you interpret that, and these are energy fluxes. But yes, if for both lower, they should be the same. It's of the substance, but if you want to maintain homogeneity and isotropy of the space itself, you cannot decouple that from the substance, what the substance is doing. Yeah. Okay, so shall I move on to the hot stuff? I should, huh? Because otherwise I'm running out of time. Okay, so the hot universe. Okay, so we're now switching to a time shortly after the Big Bang, so the first second or maybe several minutes. Okay, so as we all have figured out, if space is expanding, which means that if I turn the clock back in time, go to a very early universe, it must have been a very hot and very dense place. And then you have a lot of interactions and scattering of particles off each other. And exactly what kind of interactions you have depends on your particle physics theory. Okay, standard model for most people. And if you do dark matter, you have your own dark matter theory of how the dark matter particles get created, etc. But the most important thing when we talk about particle interactions in the early universe is the interaction rate versus the Hubble expansion rate. Because by looking at these two quantities, you can determine whether the interaction is so important that it's able to keep things in equilibrium, a state of equilibrium, or maybe it's the other way around, and the interaction is not important. Okay? So whenever the interaction rate exceeds the Hubble expansion rate by a lot, then that interaction can be taken to be in a state of equilibrium. Now, this is probably a bit abstract, but here's a classic example, and that's the weak interaction. And as it happens, it's also the most relevant interaction for neutrinos. So say you have a gas of ultra-relativistic particles, and they are all at a temperature of T. Now, I can estimate the weak interaction rate per particle, this gamma int. What I need is cross-section. And since it's weak interaction, I know this has to go like GF squared. And because I'm dealing with a ultra-relativistic set of particles, then the only energy scale that I can even talk about is temperature. So just on dimensional grounds, I can estimate the cross-section to be GF squared, T squared. Now, there's a relative velocity. That can be 1 because I'm looking at relativistic things. Last but not least, I have the number density of the scattering centers because I'm trying to estimate how a particle scatters on a bunch of stuff, okay? So this is the energy density, and again, because the only scale I have is temperature, then on dimensional grounds, N has to go like TQ. I put it all together, and what I find is that the interaction rate goes like GF squared, and then T to the power 5. So that's my interaction rate. Now, the other quantity I need to examine is that of the Hubble expansion rate. And Hubble expansion rate is this thing that I showed you earlier. I have the sum over all the forms of energy densities. There's a G, the gravitational constant, and I take the square root. Now, G in this game is normally re-expressed in terms of the Planck mass, okay, inverse Planck mass square. And the next thing I need to supply is the energy density. Energy density, again, for relativistic things, simply by looking at dimensions, must go like T to the power 4. So if I take the square root, I get T squared. So I get this estimate for the expansion rate, T squared divided by Planck mass. Now, next, I form this ratio, gamma int divided by H, and I end up with this thing. And numerically, this turns out to be about T divided by 1 MeV raised to power 3. Okay, so clearly, what this tells me is that this ratio, gamma divided by H, increases with temperature. So the conclusion I can draw from this simple exercise is that weak interactions are in a state of thermal equilibrium if I am looking at temperatures way above 1 MeV. And conversely, if I look at temperatures way below 1 MeV, then this ratio here will be tiny, in which case my weak interactions are not very effective at keeping things in a state of equilibrium. So just to give you an idea of where 1 MeV in temperature would be, it will be somewhere here when the scale factor was 10 to the minus 10 or so way before everything in the universe, way before CMB, way before large-scale structure, even before nuclear synthesis. Now, so we have established that if we're at a high enough temperature, even the weak interactions can be in a state of equilibrium. So what does that mean? Well, if I'm looking at an ideal gas, let's suppose I'm looking at an ideal gas, and say all the an interaction is in a state of equilibrium, then what it means is that all the particles that participate in that interaction will have their phase space distributions described by one of the equilibrium forms. Okay, it will be something like this, FEQ, this expression, and it's an exponential energy minus chemical potential divided by the temperature, plus or minus 1, depending on whether you're trying to describe a fermion or boson. Okay? An important thing is that all the participating particles in that interaction will have the same temperature. That's the zeroth law of thermodynamics. And the chemical potentials of all the participating particles will also have to satisfy a relation like this. So you add up all the initial chemical potentials, and they will have to be equal to the final chemical potentials if the interaction is happening at equilibrium rates. Now, in standard cosmology, the chemical potential is generally related to any asymmetry that you have between particles and antiparticles. And since this asymmetry is even for neutrinos, is most likely tied back to, well, it is definitely tied back to the matter-antimatter asymmetry, which we know to be small, 10 to the minus 10. Then for most applications, we will just set mu is equal to 0. I mean, although there are people who study what might happen if you have a large neutrino asymmetry, but for our discussion here, I'm just going to pretend that mu is exactly 0 because it makes life simpler. Okay? Now, having specified a phase space distribution like this and setting mu to 0 for simplicity, what I can do next is to determine the particle bulk properties. So things like the number density, energy density, and the pressure. And essentially, you can figure out these things by integrating the distribution function in momentum. Okay? We don't really need to worry about number density for what I'm going to talk about next, or the pressure, but just focus on this energy density. Okay, so here you have an integral over momentum, and you have the distribution F, and then it's weighted by E, which is the energy per particle of momentum P. And G alpha here is called the internal degrees of freedom, and it's essentially basically a way to count the spin degrees of freedom. So for example, for electrons, you will be 4 because you have particle and antiparticle spin up and spin down. Okay, that's 4. G alpha is 4. For photons, it's 2 because it's the 2 polarization states. For neutrinos, it's also 2 because the only way we know anyway to make neutrinos is via the weak interaction, and there are only 2 degrees of freedom that you can generate. Okay. So now I look at this energy density. In general, there's no closed form for this integral because, well, there's just no closed form in general. But I can go to the 2 limits, the ultra-relativistic limit where T is much larger than the particle mass. And in that case, rho would evaluate to be T raised to the power 4. You can also look at the non-relativistic limit, okay, where the temperature of the particle species is much less than its rest mass. And there, what you'll find is an expression like this. Don't worry about the prefactors. The main thing is that this energy density here goes like exponential to the minus m divided by t, where, as I remind you again, m divided by t is a large number. So what you can conclude immediately, just by staring at this expression, is that if you have a non-relativistic particle species which is participating in interaction in equilibrium, then the energy density of this particle species is highly suppressed. In fact, we have a name for it. It's called Boltzmann suppression. Okay? So, given this, there's another conclusion we can make, and that is, if we look at the expansion rate, h, and this thing is proportional, h squared rather, and this thing is proportional to the sum of all of the energy densities in the universe, right? But if I'm looking at this really hot universe where a lot of things are relativistic, and some things are not relativistic, then what you can do is to reparameterize this energy density here in terms of this G star parameter. So I factor out T gamma to the 4th, which is the photon temperature. And what remains, I'm going to reparameterize in terms of the G star parameter. Okay? It is a function of temperature because what things are relativistic and what particles are not relativistic depends on how hot your soup is. Okay? But no matter what temperature you look at, this G star function here will be dominated by particles that are relativistic at that time. Okay? Simply because of this Boltzmann suppression that we get once things become non-relativistic. Okay? And the G star function overall is a function of the particle physics theory that you supply. And for the standard model, it looks like this. Okay, so this is the photon temperature increasing in this direction. Time goes forward in this direction. And as you can see here, if you go to very high temperatures, then all the degrees of freedom in the standard model are relativistic. So you have a fairly large value for this G star. But as you move forward in time and the temperature drops, then you have the top going non-relativistic, and then the W and the Z and Higgs, and the bottom, and then suddenly you have this sharp drop over here, and that's basically the temperature corresponding to the QCD phase transition, where initially you may have a quark-gluon plasma at very high temperatures, but once you hit the QCD scale, everything becomes confined, and you have bound states, you have mesons and baryons instead. So you have this sharp drop over here. Okay, and as you keep moving forward, you still have some pions left because there are 100 30 MeV, so they're still kind of relativistic, but even they drop off after a while. Muons drop off, and then weak interaction goes out of equilibrium around here, and after that, the plasma is in the hundreds of keV range, and here, even the electrons and positrons become too non-relativistic to contribute to G star, so you see another drop over here. And what's left in the end are just the things that are very light or exactly massless, so photons and neutrinos, and these are these are the particle species that are contributing to the G star parameter. There are also trace amounts of electrons and nucleons and nuclei left. By small amounts, I mean something that is of order 10 to the minus 9 relative to the number of photons that we have. Okay. Now, so next few minutes, I want to concentrate on looking at this region over here. So roughly temperatures between 10 and 0.1 MeV, because that's the region that is most relevant for neutrino physics. Okay, and that is because that's when the C nu B was formed. So as if you went to my colloquium yesterday, essentially the idea here is that if you're at a high temperature above about 1 MeV, then the weak interactions are so strong that you're able to keep neutrinos in a state of thermal equilibrium through their scattering on other neutrinos and on E plus and E minus. But as you let the universe cool, then at some point these neutrinos will decouple from the cosmic plasma, and because they stop interacting, and they will free stream to infinity. Okay, so I wanted, so that's the cosmic neutrino background that you create. Now, I want to just look at this scenario in a bit more detail. And so first of all, let's examine the particle content at a temperature between 0.1 MeV and 10 MeV. Okay? So as you saw in that G star picture earlier, there are really only just a few things that are left left behind and have not completely been Boltzmann suppressed when you get down to these temperatures. So on the one hand, you have the three families of neutrinos and the antineutrinos, okay, over here. And on the other hand, you still have a bit of this QED plasma consisting of electrons and positrons and photons. Okay, remember that the muons are long gone. Okay, they're too heavy. Taus, whatever, they're all long gone. So just E plus, E minus, and gamma left behind in this temperature range. Now, these things are, all interacting and scattering off each other. So in a QED plasma, you have all sorts of QED processes. I've just listed these 2 by 2, 2 to 2 processes. I'm sure you can come up with more complicated processes. In the neutrino sector, the neutrinos can scatter off each other, which is via the weak interaction. And these are all in a state of thermal equilibrium if the temperature is sufficiently high. And importantly, these two sectors are coupled because the neutrinos can scatter off the electrons and positrons. You can also have this kind of, nu bar going to E plus E minus and vice versa. And these interactions too were in a state of equilibrium if you go to a sufficiently large temperature, larger than 1 MeV. Now, when the universe cools, what's going to happen is that these interactions will drop out because they're not sufficiently fast, sufficiently efficient, but these one will still keep going, okay? So that's interesting. So what we can do now is to set up a timeline for the thermal history of the neutrinos, okay? So we're going to look at the events, the neutrino temperature, and the phase space as we move forward in time. So first of all, what do we have? If we're looking at a temperature that's very large, then the neutrinos are coupled to the QED plasma at a temperature above 1 MeV. Okay, that's because gamma int is larger than H. And as we said earlier, when you have things in a state of equilibrium, then the temperature of these order particles must be the same. So we have this relation where T nu is equal to T gamma. Because the neutrinos are in a state of thermal equilibrium, being kept in a state of thermal equilibrium, they would have a Fermi-Dirac distribution. And in fact, because these neutrinos at 1 MeV temperature are so ultra-relativistic that we can even approximate this distribution to be a relativistic Fermi-Dirac distribution, where we replace the energy here with momentum. Because they're so fast, you don't have to worry about their mass. Now, what's going to happen next? Next is that at 1 MeV, neutrino decoupling happens. That's because at about 1 MeV, the interaction rate is roughly equal to the Hubble expansion rate. And then beyond that, gamma int will go below H. And so the neutrino sector and the QED sector are decoupled. But if you look at the temperature of the neutrino sector, it will remain the same as the photon temperature for a while, even after decoupling, because nothing's happening. Things are just evolving forward. Okay, nothing's happening. So they keep the same temperature, even though they don't really have to be, because they're not really coupled anymore, but they happen to be, yeah, because nothing else is happening. And the distribution also remains the same. But then, if I move down to a temperature of about 0.5 MeV, so that's roughly the temperature equal to the electron mass, I have another interesting thing happening. And that is E plus E minus annihilation. So what's happening here is essentially the following. So normally you have E plus E minus going to gamma gamma and gamma gamma going back to E plus E minus. And the forward and backward processes are both occurring very frequently. Okay? That is the case if your temperature is high enough. But if my plasma temperature drops below the electron mass, then I have trouble making the first process happen. Yeah, because my photons are no longer sufficiently energetic to even make an electron and a positron. Okay? But the forward process, this E plus E minus going to gamma gamma, that's still okay. Okay? It's only the first one that's not allowed. It's kinematically forbidden. So that's interesting, because right suddenly, what you're doing is that you're dumping all the energies that were, energy that was initially in E plus E minus into photons. And so in effect, what you're doing is that you are reheating the photons, okay, and making the photons more energetic than before, okay? And this is interesting for neutrinos, because it means that once E plus E minus annihilation is over, the neutrinos will come out a little bit colder than the photons. And in fact, you have this funny factor 4 divided by 11 raised to the 1/3 here, okay? But the phase-space distribution will still remain the same. And what I'm going to do in the next, so that's basically this drop here. And what I'm going to do in the next 2 minutes or so is to explain roughly why you have this 4 divided by 11 factor. And to understand why you have this 4 divided by 11 raised to the 1/3 factor, we first of all need to briefly touch upon the idea of entropy, density, and conservation of entropy. Okay? And entropy, co-moving entropy density is defined in this way. And basically, you just take the energy density and the pressure divided by the temperature, add up all the particle species, multiplied by a scale factor q, you get the co-moving entropy density. And the point here is that if the universe is expanding in a quasi-static way, so that at every stage equilibrium is maintained, then the co-moving entropy density S is approximately conserved. Okay, so if I go back to the schematic of my co-moving observers and look at the S here in each box, it's always the same S. And this is very powerful, because now we can use this idea to figure out what the neutrino temperature should be. Okay, so again, look at this picture here, where on the left-hand side, I tell you the properties of the QED plasma, and on the right-hand side, I tell you about the listed properties of the 3 families of neutrinos and antineutrinos. Now, as I said earlier, and this here is the time, so we move forward in time as we go down. And 1 MeV is neutrino decoupling. This line here corresponds to the time of E plus E minus annihilation. So everything above is happening before E plus E minus annihilation, and everything below is happening after E plus E minus annihilation. Now, in the boxes here, what I'm calculating is the co-moving entropy density in that sector. So here, this box, SQED, is the entropy density in the E plus E minus and gamma. And you can just apply the expression I showed you a couple of slides ago to figure out what this is. And you see the 11 divided by 45, and then pi squared, blah, 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 etc. Okay? Similarly, you can do the same thing with the 3 families of neutrinos, and this is what you will get. And I think I forgot to multiply this by 3, but it doesn't really matter in the end. Okay. The key point here is that before E plus E minus annihilation, the QED sector has the same temperature, T gamma here, as the T nu in the neutrino sector, because they were kept in a state of equilibrium, right? Remember that? And then even after decoupling, they kind of maintain the same temperature for a little bit. So these 2 temperatures are the same before E plus E minus annihilation. Now I go to the bottom half and look at the state of things after E plus E minus annihilation. But in the QED plasma, I have something a bit different now, because after E plus E minus annihilation, the only thing that's left are the gammas. So when I calculate SQED, what I'll find is that instead of 11, I'll have 4. Okay? It's just simply counting degrees of freedom. The rest of the expression looks kind of similar. For the neutrinos, nothing has really happened. It's still massless stuff. You still have 3 families, so the entropy degree of freedom, the Coulombic entropy density still looks like the same expression. Now, having these 4 expressions, I can now play some games. First thing I'm going to do is to demand that the entropy be conserved in the neutrino sector. Okay, and I can do that because after decoupling, the neutrinos are just isolated, and I can demand that the entropy is conserved in this isolated sector. What I'll find, so what I'll do is that I say S nu post E plus A minus annihilation is equal to S field pre. And what I get immediately is by equating these 2 expressions here is this relation for how the temperature in the neutrino sector should evolve. Okay. So that's the first relation. The second thing I'm going to do is to demand conservation of the co-moving entropy density into QED plasma. This one is a bit more interesting because these expressions are different. And what I'll find when I equate these is that the post-annihilation T gamma picks up this factor of 11 divided by 4, 1 cubed. There's still a little bit of stuff here that's a little bit funny. I have to do a bit more work. But first of all, I have this T gamma pre-annihilation, but I've already told you that before annihilation, the gamma temperature is the same as the neutrino temperature. So I can just replace this with the neutrino temperature. Another step is to make use of the expression from the previous slide about how the neutrino temperature should evolve in time. And what I get immediately is T nu post, basically just replacing this with T nu post. And if I just do a bit of massaging, what I'll get is this famous expression between the C nu B and the CMB temperature. And you have this 4 divided by 11 raised to the 1/3. And as you can see, it's really a result of the fact that E plus E minus have disappeared, essentially from the plasma, bringing this prefactor from 11 to 4. And okay, one more thing. What am I saying with this slide? Okay, oops. Yeah, so that's the temperature. Now, just a word about the phase-space distribution of the neutrinos. So as I mentioned earlier, when you produce the neutrino background, the phase-space distribution is essentially a relativistic Fermi-Dirac distribution, right? Because the neutrinos are ultra-relativistic. So you have this P divided by T nu, blah, 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 okay? Now, because the C nu B is decoupled already, it does not scatter anymore. The only thing that can happen after decoupling are the following. The temperature can redshift like 8 to the minus 1. Okay, that's basically the relation that I showed you in the previous slide, that T nu scales like 8 to the minus 1. Another thing that's happening is momentum redshift, because if the neutrinos are just traveling on geodesics, then the momenta will scale like 8 to the minus 1. But look at how P and T enter into this expression for the phase space distribution. You have P divided by T. Okay? So basically, the effects of the redshifting in the temperature and the redshifting of the momentum will just cancel out. So what this means is that you can keep moving forward in time, but the phase space distribution of the neutrinos will always remain the same. Okay? Even after the neutrinos become non-relativistic. Okay? So there's some confusion sometimes in some sectors of the community. People will feel like, if your neutrinos become non-relativistic, the phase space distribution should change. It doesn't. Okay? That's the heuristic argument, but you could actually apply the Liouville's theorem to convince yourself that this is simply a consequence that in a conservative, if particles moving in a conservative force field, the phase space trajectories don't cross. Okay, it's really just Liouville's theorem. So the phase space distribution remains more or less like a relativistic Fermi-Dirac distribution even today. And so I can use this and the expression I showed you earlier to calculate the number density. We have a relation between T nu and T gamma, and knowing that the photon background is 2.725 Kelvin, I can establish that the neutrino background is 1.95 Kelvin or 10⁻⁴ electron volt. And putting all these together would allow us to calculate the number density, which is about 112 per cubic centimeter of neutrinos and antineutrinos per family. One more thing, that was number density. The energy density is a little bit trickier, and that is because recall that the energy density is composed of where you integrate, and then you have to integrate the phase space distribution, but you have to weigh it by the energy. And things can be very different whether you're looking at a ultra-relativistic set of neutrinos as opposed to a non-relativistic one, because as we know, rho goes like 8⁻⁴ if it's ultra-relativistic, and rho goes like 8⁻³ when things are non-relativistic. And you can see that reflected in the neutrinos as well. So if we look at, see if it's actually easy to see here. So if you look at the red lines here correspond to the neutrino energy densities, and there are 3 neutrino mass eigenstates here. And what you see here is that at early times, they're all overlapping, okay? Because at early times, everything is ultra-relativistic, so the energy density of the 3 mass eigenstates all evolve in the same way. But then as you go to larger and larger scale factors, or later and later times, you begin to see a difference between these 3 mass eigenstates, because now the neutrinos are one by one going non-relativistic. And then you can see here that they kind of drop, they split up into 3 different branches over here. Another way to see this probably a little bit more clearly is in this plot over here, where I'm plotting the reduced energy density at each time. And you can see here, the 3 red lines here are the same, and essentially tracking the photon energy, reduced energy density, the green line. But as you move forward in time, these 3 things split up, okay? But the lightest mass eigenstate, which is actually has a mass of 0, is still tracking the photon energy density because they're both relativistic. But if you look at the massive states, so the thick red line over here, this one is now tracking the purple line, which is the CDM density. So what it's showing here is that it starts off as a radiation, but then slowly this massive neutrino becomes a matter. Okay? You can write down expressions for these as well. So in early times, this is the energy density relation between the neutrinos and the photons if the neutrinos are very, very relativistic. But at later times, the energy density actually goes like the mass times number density. And if you go to the present day and calculate what is this omega nu, this reduced energy density, what you'll find is that this goes like the mass divided by some factors. And I think that's it of what I want to say. This is just a summary of the C nu B. And I will continue with precision C nu B tomorrow. Thanks. Sorry for going over time.
Thanks, Yvonne. Questions?
So why was the individual entropy being conserved, like QED entropy separately and neutrino entropy separately, and not the sum of the total entropy being conserved?
Actually, there are many ways to do this calculation. You could have arrived at the same thing by looking at the conservation of everything at the same time. You would have arrived at the same answer, actually. But I did it like this because I think it's a bit cleaner. And also what is justified is the fact, what justifies my approach here is the fact that you have 2 isolated systems. The neutrinos are, after decoupling, which happens way above, and decoupling is here, I can assume that the neutrinos don't talk to the photons anymore. And if they don't talk to each other, there's no way to transfer entropy.
Yeah, but like before decoupling, since it was a single thing, so...
Yeah, if you're looking at before decoupling, then yes, you must look at everything as one single system. But after decoupling, which is what this whole scheme is, this schematic is about, I can talk about neutrinos and QEDs separately because they don't talk to each other anymore. Yeah.
Yeah, so when you were writing this h square equals to 8 pi g by 3 sum of the density. So there we assumed the flat space.
Yeah.
Right? Now, I wanted to know, what is the measurement which confirms that at that point there were no curvature corrections to that?
Well, of course, we don't really have a measurement as such, but we know we live in a fairly flat space today. And I know that curvature scales like 10⁻². Curvature energy density scales like 10⁻². Radiation energy, on the other hand, scales like 10⁻⁴. So given what I know today from CMB measurements, so I know about the energy density in radiation and the curvature, how it's bound, I can go backwards in time and establish that at these times, the curvature part should not feature at all.
So it's an extrapolation, right?
It's extrapolation. But the thing is that we have nuclear synthesis, for example, that agrees with this picture. But of course, there's no way I can go back and measure the curvature. But I think it's the only way I can see it is through the expansion rate. And what we know is that the expansion rate that we have deduced for that period is consistent with the energy density being dominated by radiation, not dominated by matter, not dominated by curvature.
So it depends upon the scale factor at that time.
Yes,
so
exactly. It's just a scaling. It's just a scaling, like 10⁻⁴ versus 10⁻². And yeah.
At that time, that's the point, right?
Well, the scale measurement of the scale factor, well, you don't really, how do I put it? Okay, scale factor is a function of time, right? You don't really measure the scale factor as such. It's, yeah. Well, I mean, how should I put it? No, it's simply that if I know what the conditions are today in the universe, and I ask, what do I need? What does the scale factor need to be to attain the conditions that we need to thermalize neutrinos or to make elements or whatever? What you immediately know is that the universe must have been a lot smaller. Things must have been a lot denser. Okay, so and from that, and then I know what the curvature is today, and I apply the scaling of 10⁻², 10⁻⁴. I would conclude that curvature shouldn't have matter.
From zero.
So again?
I remember some vague argument from long ago that if the curvature were not zero, then at some point then it would deviate even more from zero now.
Yeah. But
So
that's the reason why they invented inflation.
Yeah.
That's the reason why they invented inflation, that if you have some tiny bit of non-zero curvature, even after the Big Bang, it would blow up.
So the fact that you don't find curvature to be would that be an evidence just to say that it wouldn't have been?
Yeah, I mean, I think that's what I'm saying, right? Isn't it? Yeah, but the thing is that if you have, I think there are two things here. So if okay, so what you are saying is that, I think so people estimated that if you have a tiny bit of curvature at the gut scale, and then you allow this 10⁻² scaling to kick into place, then today you have a curvature parameter that is way beyond 1. Okay? So now I go back, and which is why they invented inflation, to push down the initial curvature to something that is minute, like I don't remember the number, 10⁻60 or something. Okay, so that's one thing. The second thing, to answer your question, is basically the same argument. I know that the curvature energy density parameter today is 0.01 or less. Then I apply the 10⁻² scaling back to set of 10 to the 10. Okay, then what I'll conclude is that radiation must be larger.
Okay.
Let's thank
Let's thank
Yvonne again.